I met some of you at dinner last night and introduced myself very, very briefly, but I thought I'd spend just a little bit of time talking about a little personal history about how I got to where I am today, because I think it's a little bit insightful relative to the positions where many of you are, I think, right now in terms of just entering graduate school, or some of you I met last night thinking about exiting relatively soon as well. But I first looked at alternative energies in 1976, in fact. I wrote a paper on solar energy. I was in high school, probably before many of you were born, I guess, a long time ago. And that was just a few years after the Solar Energy Research Institute was actually founded in Colorado. That's what NREL was called back then, before it was changed to a national laboratory in the late 80s, I guess. I went down a very, very technical pathway. I did an undergrad degree at Harvey Mudd College down in Southern California, and then flipped coasts and did a PhD in chemistry and materials, but with a very interdisciplinary approach. I did classes at the Woodrow Wilson School of Public Policy. This is at Princeton, and also in the engineering school. And went from there and did 2 postdocs in Europe. One was a NATO NSF-sponsored fellowship in Belgium, where I met a gentleman last night from Luxembourg. So it gave me the great opportunity to go to Luxembourg. So that was fun. And there I actually transitioned from chemistry and solar materials to high-speed optoelectronics and electronics, and did basically quantum-based material science in high-speed transistors, which also is the same material systems which are lasers, which actually tend to be the same material systems which are very high efficiency concentrating solar cells. So it's fairly interesting how all of that worked. And then I went on and did a postdoc at IBM in Rüschlikon. You might understand it as Zurich, Switzerland. That's the lab where there are 2 or 3 Nobel Prizes. The first one for superconductivity. I think the second one was for a scanning tunneling microscope. And did work there, and actually developed the first 980 nanometer pump laser. So it's a laser that enables an erbium doped fiber amplifier, which all of us have reaped the benefits of since about 20 years now, 15, 20 years, because that's the key amplifier in all of our fiber optic communication. And that's what allows dense wavelength division multiplexing in the optical telecom world. And so that was a pretty different pathway than where I'm at today, because I came back and worked in the lab, was a postdoc at NREL for a long period of time, and then decided I wanted to do an MBA and do more interesting things around the business and the policy and the finance side of the house. And so I did that while I was a postdoc at NREL. And that has led me down a very different pathway since then. That was maybe almost 10 years ago. And to the point where I am now as the executive director. So there are many pathways to get to follow in your career, and not one is absolutely right. But I think go with your passion, and certainly the opportunities you have here in the multidisciplinary programs, as well as the depth that you have in the technical areas, as well as the business school and the law school, et cetera, are really a unique opportunity, as well as what we do together as a collaborating institution. So hopefully that helps provide a little bit of background. So I'm going to not give a technical talk, but give more of an overview of what the Joint Institute is trying to do, and some examples of our research, and then I'm happy to answer lots and lots of questions about anything that might come to your mind. I always come back to kind of a baseline definition of, so what is sustainability if we're talking about it? This one always reflects well with me. I also reflect back on, particularly for those that are familiar with Native American history, the idea that they always considered 7 generations impact in their decisions of going forward. And so this just kind of gives a little bit of baseline. When I talk about sustainability, what do I mean? And you all may have different definitions, but this is just one that I come to. Oops, sorry. Got to get the pumping right. I'm not sure if folks have talked about kind of the evolving or current and evolving policy framework for energy and sustainability, but this is the triad of really policy issues that we are really trying to grapple with. They're very complex. From the standpoint of U.S. and intergovernmental policy, they have resided typically in one of these circles, or ovals, I guess. Typically, it might be energy security. It may have been an environmental driver. And it might be economic drivers. But today, I think you see, at least I see, that all three of these are incredibly important. And it is a very, very difficult challenge to find policies and solutions which address all of them simultaneously with all the stakeholders. And it's really that last part of that phrase which I think is most important, because putting energy decisions into place, into practice, is incredibly complicated given the social systems that we have. How are decisions made from bottoms up through top down, different regulatory, legislative, cultural environments is very, very important. And it's the recognition of these challenges, in fact, that we're trying to bring together into the mix of market, technology, and policy sciences, basically, in order to inform decisions. So the Joint Institute was formed with this strategic intent: transdisciplinary, cross-disciplinary teams to create credible, objective data, information, and insights in order to move the energy system locally and globally towards sustainability. That's a very lofty strategic intent and goal, and it's very much a challenge. But we embrace the challenge as well as the opportunities of doing that. And these are the 6 institutions which are involved. Richard mentioned them. These are the 6 institutions which found or form the core of the alliance, which is the governing body of NREL. And so it's my pleasure to work with representatives from each of those institutions and actually help build a research portfolio that tries to take a different view of looking at energy and sustainability to complement all of the work that is done deeply in the technical areas or individually in either the business schools or the law schools or elsewhere. And the conceptual idea of the program is to build out from the efficiency and the renewable expertise of NREL. To give you a sense of that, NREL has about 2,500 staff at this stage, including some temporary contractors, et cetera. About 2/3 of those are in the technical sciences and cover everything from basic materials to solar to biochemistry to geothermal, energy efficiency, a significant amount of analytic work, advanced transportation, batteries, fuel cells, and I probably forgot 3 or 4, but it's the gamut of efficiency and renewables there. But to complement that with both technical areas that reside in the universities that don't reside at NREL, as well as competency areas like the law schools, the business schools, and in particular, I think the social sciences, just coming back to my piece. And then if we're missing something, we'll go out to international affiliates. And the scope, of course, as I said, is global. Our hope and our drive, of course, is not only to do fundamental research, but to translate that research through either focus studies and education into impacts. And that's to help build a community of people who think more broadly, think about sustainable solutions, but have quantitative, deep technical knowledge and understand credible, objective information and analytics. This is particularly important in countries where there's not a lot of capability in energy analysis to help inform decision making, either at a local level or at a national level. And therefore, the education mission and the partnership with the universities is really very, very critical. I'm going to go through a couple of examples. So we have a couple of threads of research on how we do that. One thread is called Innovative Research Analysis Awards. The acronym is IRAP. You might see a poster around or so because there's a current call for proposals out there that many of your prospective or to becoming faculty hopefully are thinking about. And these are very much in partnership with each of the universities. And they call for this type of research. Again, interdisciplinary, interinstitutional, with focus toward impacts that can be really transformative. They're small, they're relatively relatively exploratory at the front end and hopefully lead to much bigger things going forward. But they get the dialogue going. And I think that's one of the most interesting opportunities is to formulate dialogues across different institutions and different disciplines, which this gathering, I think, is just really wonderful, and I have to congratulate Stanford for putting it together. So really very well done. That portfolio right now is about 10 projects, and this is the way that one cut at looking at what those look like, and then I'll go through a couple of examples. The major focus of many of these you see here kind of mapped out. And I'm not going to go through every one of them, but you can kind of see just very quickly what the shorthand titles are. If you're interested in the abstracts and what the researchers have set out to do, it's at jisea.org. It's an independent website, so it's not nrel.gov or Stanford. It's a collaborative website of all of us. And I'll highlight a couple of these, just the acronyms up here. RE is renewables, DR is demand response, GIS is geographic information systems. I think everything else is relatively straightforward. They have a minor focus as well. Let's see if I can get this to work. And what we're trying to do from an institution standpoint is to build that out in a balanced way. And you can see that we've got a call out now that really emphasizing some of the places where the current portfolio hasn't addressed as much as we would have hoped. So here are a couple of examples. I figure I'd start with one that has some Stanford collaborators on it. And this is relative to energy. It's an interesting, I guess, addition that I would certainly encourage you all, and it will be one of my themes coming through, is to think about other metrics, other aspects of energy. So not just energy and greenhouse gases or materials for energy, but what are the other pieces of the environment, be it land, water, air, that energy really impacts. And of course, then you've got society and economics, et cetera. This is one where there's an example of the group really coming up with a whole different way, and I'm sorry that's too small, but you can go up on the website and see a bigger one, of different metrics for water. How much water is used? What's the quality of that water? Is it potential to be recycled back either into the freshwater or out of the freshwater cycle in that region? Does it transfer between basins or not? And how sensitive is that technology to the availability of water and at what price, et cetera? So that's an example, again, trying to get the thinking beyond just energy for energy's sake, be it an electron or a fuel, but really thinking about a broader environmental footprint. That's one. Another one actually is more in the quantitative modeling area. And here, the example is actually between NREL and then on the other coast, MIT. Here, the detail is that NREL has come up with an extremely complicated, what's called a capacity expansion model of the U.S. electricity sector. What does that mean to folks that really haven't studied that? It means as you ask a question about what might a clean energy standard or a carbon cap and trade system look like in the U.S., how might the U.S. electricity system evolve underneath that policy framework? But that model itself, while being very geospatially rich, doesn't actually include the rest of the energy economy. And so one has to now look at how does one take into account that kind of policy on the whole economy and its interactions with the electric sector. And so there's a marriage now, actually a handoff between an economy-wide, what's called a computational general equilibrium model, and a bottoms-up engineering economic model of NREL. And the insights that come out of this are actually fairly significant relative to looking at economic elasticity differences between, for example, natural gas and its use in transportation or the industrial sector or the commercial sector, and natural gas and its ability to serve the electric sector. And so that's one example of how that might go forward. The other interesting one, just as an example, is this particular study. This is a different collaboration group. So this is NREL, Colorado School of Mines, and the University of Wisconsin as an unfunded collaborator there. 2 nuclear engineers and one actually grid modeler who knows renewables real well. And this was actually the topic of a 2-day workshop that we had earlier this week. And what we did was ask the question, or what they did was pose the question, are there synergies or potential synergies between nuclear energy and renewables in order, both as basically a low carbon sources, and challenges with renewable technologies, particularly for just the electric sector, are that they're intermittent and variable, and they need both to be called firmed up, so that means that you have available electricity when the sun doesn't shine or a cloud comes over or the wind stops blowing, both at a minute level, an hourly level, a daily, monthly, and seasonal level. And so the real question here that was posed was, could one configure economically a marriage between renewable energy and renewable systems and a nuclear reconfigured plant, and meet the load, and at what cost, and what would that system look like? It turns out that, according to those calculations, and that this paper will be out here in about a week or so, that you can achieve about 80% full decarbonization with a combination of this particular configuration of nuclear and renewables with a relatively optimized economic situation. And basically the answer comes through using a high temperature nuclear reactor rather than a light water reactor, storing the heat and oversizing the power block, and using the power block as a fast ramping power production unit, while the nuclear unit is run full out for its electricity, because that's where the economics of nuclear power come into play and are most viable, versus, for example, ramping a nuclear plant. So you reduce the energy output of the nuclear plant. So that's relatively interesting. We just spent 2 days on this with a small group of people, and it turns out that this is only one of probably thousands of configurations, and this one asked a question that was really only around the electric sector. And it turns out if you open your eyes a little bit, take the blinders off and ask, what about energy more broadly? It turns out if you think about fuels, fuels and chemicals, fuels as a subset of chemicals, liquid fuels, that they're actually an enormous number of possibilities, be it either using heat and natural gas or biogas into hydrogen, or just doing high temperature steam methane reforming to do hydrogen. You could think about combining this with biogas or bioplants and doing other high temperature uses of the waste heat out of the nuclear facility, perhaps putting it into methanol and or other chemicals as well. And so that suite of opportunities is actually fairly large, and there are a lot of really interesting challenges with that. Here's another one, completely not in that technical realm, but more in the analytic realm of looking at the grid utility. So this is a group between NREL and the Colorado State University where they're looking at creating new what's called dispatch models. So hourly dispatch models of looking at the electric sector and asking questions about the financial business model and the rate structures. So I probably had a couple of conversations with Frank Wallach yesterday around this in his area of expertise. And this is just an exploration there. And deep questions here about how does the market and regulatory structure change relative to a a structure today which literally is based upon selling of the energy, an electron, versus capacity or services or surety of that ability, and or other what's called ancillary services in the market, so be that voltage or spinning reserve, frequency reserves, and things like that. So the details of the electricity markets, and can one derive value out of those in a much different way than they are structured today in order to support a transition toward a system that would be much more sustainable. Completely on the other end of the spectrum, this is more to folks that are studying electrical engineering. This is a group out of Colorado School of Mines and Colorado State University, where in fact they've used a benchmark mini grid to look, a microgrid to look at dispatch algorithms for renewable energy and actually embed artificial learning into those algorithms for optimization. So very computationally intensive. It's a kind of a marriage between an electrical engineer and a computer scientist moving forward, and so that's another interesting example as well. Here another Stanford opportunity here with the Stanford collaborator and actually MIT, where they're looking at productive uses of CO2 and doing a fair amount of broadly environmental metrics analysis of that. I think Jennifer, I don't know, Jennifer, did she ever come and talk? No? No? Okay. So you could talk to her on campus, I guess. And Adam and others as well on that team. Yeah? Okay. Oh, I thought I eliminated that. I'm going to skip through that one because of a lack of time, because I want to get to a couple of other things. Here's another one, again, computationally intensive, looking at GIS mapping. So thinking about how do you optimally place potential or identify potential sites for solar, or it could be wind or geothermal, et cetera, starting with the solar resource and then a number of filters down, and then thinking about some of the social aspects as well. So again, it's a mechanism as well as a website and enabler for some local organizations to be able to look at their potential opportunity in their county or state and region. I'm sorry, we didn't get too hard. I'm going to do two other quick projects and see how fast I can get through them, so I can leave plenty of time for questions. One actually is a project that started when I had an old hat on. It was renewable centric, but it's a real example of the Joint Institute working with a global collaborative team, and it's the representation of renewables in integrated assessment models, so the climate assessment models, which I think is important, and I'll glance through that real fast, and then talk to you a little bit more about energy and water and why that's so important. So this group here, my prime collaborator is John Wyant, who I don't think was on the agenda. Is he on tomorrow? Oh, great. Okay. So he's an incredibly busy man. And so it's a pleasure that he's been able to find some time both to be on my program committee, but also to help me with this piece as well. And lots of other collaborators from around the world now, and linking with more than 40 integrated assessment modeling teams. And the key issue when I think about renewables, or when we got together to think about renewables and these climate or integrated assessment models, is that many of them have algorithms in them based upon, in some sense, a little bit of ancient history. There used to be, I'll call it a myth, that variable renewables can only really supply about 20% of the electricity or the energy system, and that was basically, it was a hard stop put on those penetrations in a lot of those models that were, have been developed now for 20 or 30 years, or that they require one-to-one backup. Which also isn't true when you look at the nitty-gritty detail of how these things operate. Many of them don't include many of the emerging renewable technologies and or currently just being expanded commercially, like offshore wind, which is really actually quite commercial in Europe. And the first couple of plants have been approved and are being built here in the United States as well. And so it's a little bit of a disservice to that particular opportunity to not allow it to contribute to climate mitigation, for example, under a climate mitigation scenario. The wind resolution piece I'm going to actually show you in some detail, and then a couple of other pieces. So there's some goals here. You can read that very, very quickly. The idea is to really help improve that fidelity for these models and then move on to efficiency and a bunch of other different technology areas. But really to help move that into the system because, as you know, as Richard mentioned, I'm part of the IPCC authoring community, and there's some real opportunity there for the next assessment report and the impacts that not only those reports have, but what the modeling community has in general. Let me just show you some examples here. So this is a wind resource map of Indiana at 50 meters hub height. The darker purple is higher wind speeds. And so if you look at this map, you would say in general, where it's kind of yellow and a little bit orange, that there's not a whole lot of wind in that particular state. Here, if you actually look at it at 70 meters height, this is height above ground, you come up with a very different picture. And if you look at it at 100 meters, you get even a very, very different picture. And I'm going to guess that somebody knows that current hub heights are 80 meters above ground, at least onshore. They're higher than that offshore. They're actually limited by the size of both the turbine blades themselves, as well as the towers that can fit on trucks and fit underneath the overpasses on rail and or on roads. And so there's a lot of innovation going into thinking about how do you do smaller components and actually get them to be robust. But the difference here is, of course, that if you use 50-meter hub heights, you don't get the right wind resource, and that really impacts the economic analysis going forward and the information that's being provided to decision makers. The horizontal scale also matters incredibly much. So here what you see is a 50 by 50 kilometer grid cell. It's a test cell. This is done by collaborators at Riso National Laboratories in Denmark. And on the upper left here, that's the 50 by 50 done at a 10-kilometer resolution, so that's 25 little cells in there. And that's analyzed. And so here, the scale, and I apologize, higher green is higher wind in terms of just wind power now. Here you've got 5 kilometers, 10 kilometers, and about 90 meters. And what you see, as expected, really, just kind of rationally, is that the finer resolution, you get more expression of the underlying terrain, right? Because wind basically has a boundary layer with the terrain, and it's windier on the ridges than in the bottoms of the valleys, et cetera. And that comes out here. This is just a visual way of showing that analytically. But then the question, of course, is, okay, so great, that's a nice map, but what does it mean economically? And here, let me just show you visually what that looks like at a country level. So this is the 50-meter hub height map of the United States. It's produced by colleagues at NREL. This is the 80-meter hub height, and you can see there's a bit more wind in the middle. It doesn't include the offshore on this one. But if I overlay the 50-meter with a global data set, because global climate analysis is done globally, but you need a global data set. So the global data set actually is that data set which is in dots. And you can see in principle that that's pretty poor resolution. That's hundreds of kilometers versus I think I just showed you about 90 meters. You'd actually like it finer than that even. And in particular here, where it's the windiest part of the country, you can see that that global data set, any of these dots in here, never pick up the high wind quality. Never. And in fact, you see that now. If we take all that data in a big data set, and we actually calculate the number of square kilometers of wind as a function of wind class, where class 7 is the highest quality of wind, i.e. the windiest area, and class 4 and 3. So these are the ones that the wind developers really look at. They're the ones where they make the most money. And so here you've got 4 curves. The red one, which is based on those dots, the orange, kind of brownish one, is 50 meters hub height. That's with exclusions. So that means you take out very steep slopes. You take out land which you can't build on, like national parks or environmental exclusion areas and things like that. And then you've got 2 others for 80 meters as well. So you can see the difference between 50 and 80 meters. And so why is that important? Because this is effectively an economic supply curve for those models. And if we were to have used the coarse scale data rather than the fine scale data, we would miss 750 gigawatts of wind. And so the US electricity system today, anybody have an idea about how big that is? Top of your head? give or take 900 gigawatts, I think, roughly. So you could essentially, and I'm not saying that that's equivalent, but that's a lot of wind out of about a total technical resource potential of about 9,000 gigawatts. And so that's the least cost, highest value added wind. And if it's not in those economic models, we've actually done ourselves a disservice. And so what did we do? We worked with an international team. And this is a graph out of our partners at IASA, the International Institute of Applied Systems Analysis, which has a wonderful young scholars summer program, YSSP, for those that want to think more broadly. It's housed in the summer castle of the royal family. And IASA was actually formed as a collaborative institution of the National Academies of Sciences post-World War II in order to train and engage Russian science. Is it World War II? Is that right? I think, yeah, World War II. To train scientists and to build scientific collaboration. And it's a wonderful opportunity to go, and I encourage you to look at their website and see some of their work. Anyways, what we did with them, and they have a model. They have one of these integrated assessment models which has some very rich detail and opportunity. What we did with them was do a kind of a first experiment on this question of whether or not the wind resource data, way at the early end of an economic model, actually makes a difference or not. And here you see the results where they've compared old wind data and new wind data under three basic types of scenarios: a baseline, which is kind of business as usual under a policy environment, and then two climate stabilization scenarios, one at 450 parts per million CO2 equivalents, and the other one at 550 parts per million CO2 equivalents. And the only result out of the whole global economic analysis that they've done is extracted out the onshore wind component for Europe. And so here you see under the business as usual, where there's not very much economic drive for developing wind, is that it kind of maxes out at about 7 or 8 exajoules. And under 550, where there, again, there's less push, it grows a little bit. But interesting, under 450, where the model wants to economically build as much low carbon energy as it possibly can to be at least cost, it used to max out at about 11 exajoules because essentially it had no more economic wind to develop. And when you change the wind resource, so that's the difference between the old curve and the new, you actually see about 2.5 times more wind economically developing under this kind of scenario projection. And that's relatively significant because that's actually a lot of wind. It's a big difference. It should make a difference actually in the economics of climate mitigation as well. And when you ask that question, you come up with actually an indication that the economics of mitigation is actually fairly sensitive as well. So this is a result from a different collaborating group, did the same experiment, but they ran it all the way through the global economic calculation of percent of gross domestic product or gross world product that it costs in order to reach those mitigation targets. And here you see the results with the old wind the old wind resource and the new wind resource, and you see about a net 10% decrease in the cost of mitigation. So this gave the group confidence that it was a very important thing to do, and then we keep going, and we have a lot of work yet to be done. This is actually, I'm going to switch here real fast for 6 or 7 minutes while I can, and then get questions. So this is actually a really interesting reflection on the fact that not only do 1.4 billion people not have access to modern energy, but also about 1 billion people don't have access to modern water. And so, why go to water when this is an energy week? And so the question, of course, is, why not? Actually, I ask. And so let me give you a little bit of background. Turns out at a global level, we have current demand at about 4,500 billion cubic meters a year. the available supply is less than that. So at a global level, if you believe the numbers where this comes from the Stockholm Environment Institute, et cetera, we're already in an unsustainable situation globally on water. Now, it doesn't mean that you can't do a lot more recycling and you can't look at desalination, et cetera. But on the freshwater supply, things are very, very constrained. The projections out to 2020 are fairly stark as well. And we'll just keep going. And what's the connection then with energy? All sorts of connections, really important connections, all the way from power to oil sands, unconventional gas, mining, and renewables fit right in there, particularly on biofuels, but also solar as well. You saw a couple of examples of our research teams, which are looking at that linkage as well. So here's an example, just to give you a sense on water withdrawals. There are a couple of key metrics. Withdrawals are different than consumption. So just want to make sure that's really clear. This is withdrawals. It just gives you some numbers. It's 50% of our U.S. withdrawals are for power. Now, not on consumption, so I'll flip through that. And it's give or take about 50% globally. That's pretty significant. Depends on what you do with it. How much water does it take for a power plant? The numbers are here. It's pretty stark. That's a lot of water. If you think you're doing a good job by, conserving at home, the home use of water does add up, but it's pretty small, both compared to the industrial sector, but also the agricultural sector in particular. But those metrics actually have been improving. This just gives you a sense of where the thermal power plants are today and what their relative consumption is of water as it goes through. This is based on collaborations with the National Energy Technology Laboratory and EIA. 71% of total water withdrawals today in this country, and maybe more so globally, come from freshwater sources. You'll note that most thermal power plants are located next to rivers or to lakes because that was what was available when we built those, and that is actually what's available today because it actually costs money to get into the aquifers, and the technology was really derived around having water availability for the efficiency of those thermal cycles. This, again, withdrawals, let me contrast that. You can tell actually once through is the dark blue, a cooling pond is the lighter blue. There's actually a cooling tower in there, and then some others for wind. Those withdrawals contrast pretty starkly to consumption. So, thank you. The difference between consumption and withdrawals, of course, is after the water is cooled back down within some, I'll call it regulated temperature allowance by the EPA and others, that water's recycled back into that water table. So you can see that's actually fairly different. Concentrating solar is not insignificant. While we like the fact that it's a low greenhouse gas technology, but in a cooling tower situation, again, because concentrating solar tends to work off of a steam turbine, that there actually is water consumption associated with it. So we have to think about that. And there are options. You can go to dry cooling. You can do a lot of other things. This is one that I don't know if Sally, you mentioned that in your talk or not, but when you add carbon capture and storage, or the capture piece of it at least, onto a thermal power plant, at least with today's technology, and so here's a real research opportunity. Today's technology are both water intensive and energy intensive. It's about 2.5 times more water is used when you introduce an amine cycle or some other absorption cycle in order to capture the CO2. So that just kind of, in some sense, compounds the challenges relative to the water scarcity and what we're trying to deal with in terms of sustainability on the energy front as well. This is a very complicated graph. I would refer you to Jordan Machnick and all publication from NREL. So this is the life cycle sorry, not the life cycle, the total water, both in consumption and withdrawals of many, many different power technologies. I think here is just highlighting what's available and where it moves to when you add carbon capture and storage.
relative to a number of others. And it, you know, you can pull out lots of different messages on here. I think the interesting message here is that every technology, I think I said this last night at dinner, every technology has its pros and cons. And I think what we have to do is come up with, you know, quality metrics across many of them and look at them all and decide in an informed way what we want to do in terms of going forward with that. And this then compares then the carbon footprint in pounds per megawatt hour or kilowatt hour and water consumption. So and the withdrawal is the size of the circle of different technologies. And so here you can see, in fact, geothermal sits out here. It's actually fairly consumptive on the waterfront, depending again on the specifics of the geothermal plant and a bunch of others. So kind of killed that to death. Let's see here about the balancing act. So this is actually a graphic I stole from the World Economic Forum. I actually think it's kind of nice just to kind of sit back and reflect. So I talked about water. They actually took a bigger picture, and it's work that I'm involved with a number of other folks these days, which is actually energy, water, food, climate, et cetera. And I think we need to just kind of map out and think about all of those interactions. So again, I applaud you for the interdisciplinary nature of the conversations and the friendships and the collaborations that you're developing this week and will be going forward. And I add in particular, I think their graphic forgot the background, which is the changing climate a little bit. And I think in specific, I really want to think about the demographics, the social issues, social media, and public perceptions and how we do make decisions. So we have a couple of studies. Give me 2 minutes. All right. That we're pursuing at this stage. So this is kind of the second track. We have kind of those projects. We've got the Innovative Research Awards, and now we've got some very targeted studies. One, again, collaboration among all of the Joint Institute partners actually is the role of natural gas in the transforming or on the U.S. energy sector, particularly the electric sector. So that's a new study looking at a lot of the questions related to the supply side of natural gas, particularly unconventional gas, so that's shale and tight sands and things like that. Everything including water, above ground issues, fugitive emissions and things like that. There's been a new twist to that introduced most recently from NCAR, which is actually looking at climate models and decreasing the amount of coal but increasing the amount of gas, and actually looking at the net radiative forcing differences with that energy shift. And it's a little less attractive than if you just look at the net greenhouse gas or CO2 equivalent emissions at the front end of at the full fuel cycle. And so that has to be looked at in some more detail. We'll go into looking at the other sectors as well. We've got the nuclear and renewable, I mentioned that, and then we've got an effort that's really just growing in terms of looking at sustainable urban environments and rethinking that framework for sustainability. So I talked to, I don't know, half a dozen folks last night at dinner who all said, I'm doing materials in solar. And then I had one question, and I won't say who said, well, I was advised that solar's kind of mature, and I should maybe think about, thinking about a different area. And so I thought I would put this up because I'm not sure if you've seen it or if you will see it tomorrow, depending on who's going to come up and present. But this is a graph that Larry Kazmersky at NREL has tracked the solar record performance of solar cells in the lab. So these are 1 centimeter, square centimeter typically cells for like almost 40 years, I guess. And here you can see it as a function of different materials, systems, as whether or not it's concentrating or not. I think I mentioned to a few of you last night, because of my background in chemistry and quantum physics and then moving on, et cetera, you actually see down here one of the first actually electrical outputs of a certified cell based upon multi-exciton generation in solution-based quantum dots. So this was a phenomena that really was new physics probably only 3 or 4 years ago and has now transitioned into a new cell that's being measured. And of course, it's very low efficiency, but the theoretical efficiency of a cell like that under 400 or 500x of concentration actually is in the mid-80s. So it's a pretty phenomenal piece, you can find this graph. Actually, I'll leave it here into those situations, but you're welcome to look at them. So those are just some concluding thoughts. From my perspective, having gone technical with an MBA and now transitioning into this kind of economic policy and finance and what we're trying to do with the Joint Institute, I think there's a real place for science in society broadly, deep science, but in context. Systems and solutions are really critical. You have to be deeply technically knowledgeable, but they have to be built up into solutions. Cross-disciplinary teams, I think I've talked about that quite a bit. And including your colleagues in the sociology and psychology departments, the business schools, the law schools, et cetera. Lots of metrics to think about, not just one or two, but really think quite broadly, ask those deep questions and the broad questions. And unique opportunities, I think, particularly at this stage in your career, to do both a deep dive, but be part of a great collaborative team. So thanks for your attention, and I apologize I ran 4 minutes over.
We have time for maybe 10, 15 minutes of questions.
On the water issue, why is it that a concentrating solar power plant would use so much more water than, say, a coal plant that's running similar systems?
So back on that graph, it depends on the cooling tower technology. Plus, a concentrating solar plant requires water for mirror cleaning, which is not something that a coal plant does. So if they are, let's say, equivalent power blocks, and they have equivalent cooling technologies, so let's say they're both once through cooled, the CSP plant will actually have more water consumption requirements because the water which is used for the mirror cleaning actually is lost because it drips off the mirror and then is evaporated out of that water basin.
Any country at this given time. Which of the three do you think the government should be more focused on? I agree it's interdisciplinary, but I mean, they have only so much they can do, right?
I would, my answer to that would be that they really have to deal with all three of them at the same time, simultaneously, the same way that you want to find solutions that deal with the economic issues, the energy security issues, and the environment. The ideal solutions actually address all of them. And in fact, if you look at many of the energy technologies that you all have heard about all week and will through today and tomorrow, many of them do offer those opportunities. But there are still some trade-offs among them.
You mentioned work being done around microgrids. I was wondering if you could talk a little bit more about what's being done in that regard.
Yeah, there's actually quite a bit of interesting research there. That's everything from looking at housing developments with intense penetration or significant penetration of photovoltaics, and whether and how those essentially distribution level grids can then work in collaboration or in sync with the larger grid, the larger basically backbone of the grid. In fact, I should probably defer this to my colleague Dave Mooney, who's going to come talk tomorrow about this in more detail. But that's one example. The other one is we have for many, many years worked on microgrids for individual communities, be them in rural areas, rural populations, et cetera. So that's hybrid systems along with microgrids. But at this stage, that actually continues, and now there's new work actually, and somebody asked me this question last night about the military and alternatives. The military are actually interested in microgrids and islanding for their bases because of the requirements, the reliability requirements of their power. And that's everything from grid integration of renewables through to hybrid systems that might have a nuclear facility in them plus renewables, et cetera. There's a lot of that. There's one behind the pole, Richard.
Hi. I'm interested in the thermal storage with nuclear as a way to offset the intermittency of renewables. What is the benefit of doing thermal storage with nuclear compared to thermal storage with CSP?
So it's a bit different. So if you look at the load duration, what's called the load duration curve, if you look at the load curve of a typical
load area. It turns out, without significantly rethinking what that load curve might look like with demand response and smart metering, et cetera, that about 60% of the load is constant throughout the whole year. And so the question is, what's the least cost, least environmental footprint way of meeting that 60%? And then how do you deal with the rest of it, including a super peak, which is maybe only a few hours a year? And if you want to look at that in least water and least carbon as an example of two kind of bounding questions, then you actually would optimize the economic outputs of the nuclear plant and then use the thermal storage with solar on the side. Can you do that by building a large power block and a large storage system with solar as well? You likely could, and the question would be, what are the relative economics of the nuclear plant and the solar plant themselves, as well as a real question on land use, particularly if you're thinking about, providing all of the power for Texas, for example, or for the western United States. So there's again a land use trade-off there that really needs to be thought through. And it's not saying that, that nuclear solution is going to be necessarily the cheapest one, but the question was, is there a synergy that we really haven't looked at before? Keep going. Would you save me 1 or 2 minutes right before the end so I can just talk about a couple things I forgot?
I have a quick question about the projects that you mentioned, both about the funding of them and kind of where the ideas are generated. Is it something that NREL comes up with and then tries to recruit out of those partner universities that you mentioned, or is it usually the other way around?
The IRAPs, the Innovative Research Awards?
Yes.
Yeah, that's a general call for proposals, so it's out now. You can go up to the website and read it. Those ideas come from the PIs, and then they're put through a review process. It's very similar to GSEP, I think, does a call for proposals, and other institutes as well. Funding comes both from the Joint Institute, but and this year there's potentially co-funding available from the university itself or from other universities. Wow, you're exhausted for lunch. Let me just mention a couple different things that we were talking about right beforehand. The first off is that we have hired multiple graduates out of Stanford. So if you have a bent toward national labs, we look forward to working with you. In some sense, throughout your graduate career, we also encourage and really look for interns and students that we can work with. If the powers that be here allow, some of our senior scientists are allowed and certainly have sat on theses committees before. Colorado's a different place than California.
So how do people pursue internship opportunities with NREL?
Part of it would be to work with your advisors here and ask them whether or not they have an existing relationship or know someone at NREL that's doing similar work and can introduce you and make an introduction. Another one would be, at least on the Joint Institute realm, would be to talk to my program committee liaison, who is John Wyant, and just knock on his door and say I'd be very interested in an internship at NREL. Can you help me? Introduce me. Let's see. Broader in the technical areas. Stuart. There we go.
And the energy club too. I mean, more and more they're posting curriculum too. The energy club is a mechanism for everyone to see what's going on.
Okay. Other one? So, I mean, that was kind of the important piece about working with us. So we've got postdocs available as folks are leaving, if they're interested in that. The internships.
Could somebody maybe introduce Stuart? Has he been introduced yet? I guess he's going to be the moderator tomorrow.
Stuart's going to be the
Stuart
moderator
plays
tomorrow,
an
but-
important role here too. Maybe if somebody could just say something about that for a minute.
Maybe.
Stuart, stand up.
Why don't you come up one thing about
Yeah, but maybe.
Go ahead.
Let me say something. Let me say something.
Okay, so I did mention before the relationship that Stanford has with NREL, and so NREL sort of has ambassadors at each of the universities, people who can help facilitate the relationship between each university and NREL. And we're very fortunate to have Stuart McMillan from NREL, who's here as a consulting professor here at Stanford and is around a lot of the time and has been here for over a year now and is still going to be around. And so he's the person to go to, I would say, here at Stanford if you want to find out about opportunities, whether it's research opportunities, internship opportunities, all those sort of things. That's probably as much as I can say. I think you'll hear from Stuart. Stuart, if you want to add something now, that's fine. But tomorrow he'll be moderating the session, so you'll have plenty of time to hear from him and speak to him tomorrow.